The year is 1940. Europe is engulfed in darkness. Nazi Germany has conquered France, Belgium, the Netherlands, Norway, and Denmark. Britain stands alone, battered by nightly bombing raids. German U-boats prowl the Atlantic, sinking supply ships that Britain desperately needs to survive. The Nazis seem unstoppable, and they have a secret weapon that makes them nearly invincible. Enigma. Enigma is not a bomb or a tank. It's a machine. A coding machine that transforms German military messages into gibberish that no enemy can read. Every day, German commanders send thousands of encrypted messages directing U-boat wolf packs, coordinating bombing raids, and planning military operations. The British can intercept these messages, but they cannot understand them. The code seems unbreakable. But in a secret facility hidden in the English countryside, a team of brilliant minds is waging a different kind of war. They're fighting with mathematics, and leading this team is a 27-year-old mathematician named Alan Turing, whose ideas will not only help win the war but will lay the foundation for every computer you use today. This is the story of how mathematics became a weapon, how one man's genius saved millions of lives, and how the foundations of our digital age were forged in the crucible of war. Alan Turing was born in London in 1912. From childhood, he was fascinated by how things worked. He would take apart toys to understand their mechanisms. He became obsessed with mathematics and logic, seeing patterns and possibilities that others missed. At Cambridge University, he studied mathematical logic and began exploring profound questions about the nature of computation itself. In 1936, before anyone had built what we would recognize as a computer, Turing published a paper that changed everything. It was titled Uncomputable Numbers, with an application to the Entscheidungsprobe. The German word Entscheidungsprobe means decision problem, and it was one of the great unsolved questions in mathematics. The question was this: is there a mechanical procedure, an algorithm, that can determine whether any given mathematical statement is true or false? Can mathematics be completely automated? To answer this question, Turing invented something revolutionary: a theoretical machine. It wasn't built from metal and wires. It existed only on paper, in Turing's imagination. But this imaginary machine could, in principle, perform any calculation. That could be described by a set of rules. The Turing machine, as it came to be called, was beautifully simple. Imagine an infinitely long tape divided into squares. Each square contains a symbol, like a 0 or a 1. A reading head sits above the tape, able to read the symbol on the current square, write a new symbol, and move left or right to the next square. The machine follows a set of rules. If you see this symbol, write that symbol and move in this direction. Despite its simplicity, this imaginary machine could compute anything that can be computed. It was the theoretical foundation for every computer ever built. Turing proved that some problems, including the Entscheidungsprobe, were undecidable. No algorithm could solve all possible mathematical questions. There were fundamental limits to what computation could achieve. But Turing also proved something equally important. Within those limits, the possibilities were endless. His theoretical machine could simulate any other computing device. It was universal. This insight, born from pure mathematical curiosity, would soon have urgent practical applications. When World War II began in 1939, Britain urgently needed mathematicians. The government, code, and cipher school, a secretive intelligence organization, was desperately trying to break German codes. They recruited the best mathematical minds in Britain, and in September 1939, Alan Turing arrived at Bletchley Park, a Victorian mansion 50 miles north of London that would become the center of British code-breaking efforts. The challenge facing Turing and his colleagues was monumental. The Enigma machine, used by German forces, was a marvel of mechanical encryption. It looked like a typewriter, but with a diabolical twist. When you pressed a key, the letter wasn't typed directly. Instead, it passed through a series of rotating wheels called rotors, each wired in a complex scrambled pattern. After passing through 3 rotors and bouncing off a reflector, the signal returned through the rotors by a different path and lit up a letter on a Lamboard. The genius of Enigma was that the rotors turned with each keystroke. Press A once, and it might encrypt to Q. Press A again immediately, and it might encrypt to F. The rotors had notches that caused them to turn at different rates, like an odometer in a car. This meant the encryption pattern was constantly changing. The same message encrypted twice would produce completely different ciphertext. But it got worse. Before sending messages, operators would set the rotors to specific starting positions, chosen from the alphabet. With 3 rotors, each having 26 positions, that's 26 times 26 times 26, or 17,576 possible starting positions. And the German military had multiple rotors available, which could be inserted in different orders. When you calculated all the possible rotor arrangements and starting positions, Enigma had over 150 million possible settings. To make it even more secure, Enigma included a plug board that swapped pairs of letters before they entered the rotors. This multiplied the possible settings by billions more. The total number of possible Enigma configurations was approximately 1 followed by 2 zeros. To put this in perspective, if you tried one configuration every second, it would take longer than the age of the universe to try them all. The Germans believed Enigma was absolutely unbreakable. And mathematically speaking, they were almost right. Almost. Polish mathematicians had made the first breakthrough in the 1930s. Marian Rejewski, Jerzy Rakicki, and Henryk Zagalski developed techniques for attacking early versions of Enigma by exploiting the fact that the reflector meant no letter could encrypt to itself. If the ciphertext contained an M, the original plaintext definitely was an M. This seemingly minor quirk created patterns that mathematical analysis could exploit. But when war began, the Germans made Enigma more complex. They added more rotors, changed procedures, and increased security. The Polish techniques became insufficient. When Poland fell to Germany in September 1939, Polish cryptanalysts escaped to France and shared their knowledge with the British. But breaking the enhanced wartime Enigma required new ideas. Enter Alan Turing. Turing brought his experience with logical machines and systematic computation to the problem. He realized that, while you couldn't try every possible Enigma setting, you could use mathematics to eliminate most of them. The key was finding cribs places where you could guess the plain text of a message. German military messages followed predictable formats. Weather reports always began with the German word for weather. Messages often ended with Heil Hitler. If you could guess even a short phrase in a message, you could use that as a starting point for mathematical attack. Turing designed a machine called the Bombe, named after an earlier Polish device. The Bombe wasn't a computer in the modern sense. It was an electromechanical device specifically designed to test Enigma settings at high speed. It exploited the logical contradictions created by Enigma's reflector and the Germans' procedural habits. Here's how it worked. Suppose you had a cribba guess that a certain piece of ciphertext corresponded to a known piece of plaintext. You could set up the bomb to test thousands of rotor positions rapidly. The machine used electrical circuits to simulate Enigma machines running in parallel. When it found a setting that was consistent with the crib, it would stop. These candidate settings could then be tested by human operators. The first bomb became operational in March 1940. It was massive, standing over 6 feet tall and 7 feet wide, containing over 100 rotating drums and miles of wire. It clicked and clattered as it tested settings, sounding like dozens of knitting needles working at high speed. When it found a possible solution, it stopped with a loud clunk. But breaking Enigma wasn't just about building machines. It required brilliant mathematical insights. Turing developed techniques called Bombe that used Bayesian probability to rule out most settings before even using the bomb. By analyzing statistical patterns in the ciphertext, Turing could calculate the odds that certain rotor orders were being used. This reduced the search space from billions to thousands. The breakthrough came gradually. At first, Bletchley Park could break only some messages, and often too late to be useful militarily. But as more bombs were built and techniques improved, the codebreakers became faster and more reliable. By 1941, they were breaking German Army and Air Force Enigma regularly. Then came an even bigger challenge: naval Enigma. The German Navy used a more secure version of Enigma with 4 rotors instead of 3. This multiplied the possible settings by 26, making naval Enigma exponentially harder to break. And naval Enigma was the most crucial target of all. German U-boats were sinking Allied supply ships faster than they could be replaced. Britain was being slowly starved. Breaking naval Enigma could save thousands of lives and turn the tide of the Battle of the Atlantic. Even your DNA exhibits fractal organization. The way genetic material is packaged in your chromosomes shows fractal structure across multiple scales, from the double helix to the compacted chromatin to entire chromosomes. In medicine, fractal analysis helps diagnose diseases. Healthy biological systems often show fractal patterns, while diseased systems lose their fractal character. The heartbeat of a healthy person shows fractal variation in the time between beats. A heart in distress loses this fractal variability. This insight helps doctors detect heart disease earlier. Cancer researchers discovered that the growth patterns of tumors often deviate from normal fractal patterns. Analyzing the fractal dimension of tumor boundaries can help distinguish benign from malignant growths. In technology, fractals revolutionized computer graphics. Before fractals, creating realistic natural landscapes in computer games and movies was incredibly difficult. How do you program a computer to draw a convincing mountain range or forest? The answer is fractal algorithms. Computer graphics artists use fractal techniques to generate realistic terrain, clouds, water, fire, vegetation, and countless other natural phenomena. The landscapes in movies like Star Wars and Avatar, the environments in video games, the computer-generated special effects we now take for granted, all rely on fractal mathematics. Fractal compression algorithms can compress images by recognizing self-similar patterns at different scales. Instead of storing every pixel, you store the rules that generate the fractal pattern. This can achieve remarkable compression ratios. Antenna engineers discovered that fractal antennas can receive and transmit multiple frequencies efficiently because their self-similar structure resonates at different scales. Your cell phone likely contains fractal antenna designs that allow it to communicate across multiple frequency bands. Financial analysts use fractal models to understand stock markets. Mandelbrot himself applied fractals to economics, showing that market fluctuations exhibit fractal patterns. Price movements at different timescales, from minutes to months, show similar statistical properties. This fractal nature helps explain why markets have sudden crashes and booms that traditional models can't predict. Network scientists found that the internet has fractal structure. The pattern of connections between computers and routers shows self-similarity at multiple scales. Understanding this fractal architecture helps optimize network design and improve internet performance. In music, composers have experimented with fractal compositions, where musical patterns repeat at different time scales. Some researchers even claim that successful music often exhibits fractal properties, with patterns that recur at different levels. Urban planners discovered that cities grow in fractal patterns. The distribution of streets, the size hierarchy of urban centers, and the density patterns of development all show fractal characteristics. Understanding these patterns helps design better transportation systems and predict urban growth. But perhaps the deepest significance of fractals is philosophical and aesthetic. Fractals revealed that complexity doesn't require complicated rules. Infinite richness can emerge from simple, repeated processes. A single equation, iterated endlessly, can generate beauty that never repeats yet maintains coherent structure. This has profound implications for understanding nature and the universe. It suggests that the vast complexity we see around us, from galaxy clusters to ecosystems to the neural networks in our brains, might emerge from relatively simple underlying rules repeated across different scales. Fractals also bridge the divide between mathematics and art. For centuries, math was seen as cold, logical, abstract, while art was emotional, creative, expressive. Fractals show these aren't opposites but different aspects of the same search for pattern and beauty. When you zoom into the Mandelbrot set and watch spirals and tendrils and miniature copies emerge, you're witnessing pure mathematical truth. Yet the experience is deeply aesthetic, emotionally moving, even spiritual for some people. The patterns are beautiful not by accident or human design, but because mathematical truth itself possesses inherent beauty. Artists have embraced fractals. Fractal art has become its own genre, with artists creating stunning images by exploring different fractal formulas, choosing color schemes, and finding compelling views within infinite mathematical spaces. But you don't need to be a mathematician or computer programmer to appreciate fractals. They're all around you. Look at a fern leaf. Notice how each frond looks like a miniature version of the whole leaf. Observe how a tree's branches split into smaller branches that split again. Watch lightning fork across the sky in a fractal pattern. Study the intricate boundary of a snowflake under magnification. Nature has been creating fractals for billions of years. Evolution discovered that fractal designs efficiently solve many challenges, maximizing surface area, distributing resources, adapting to different scales, creating robust structures. Life itself is fractal, and when you breathe, fractal airways fill your fractal lungs. When your heart beats, fractal vessels carry blood through fractal networks. When you think, fractal neural structures process fractal patterns of activity. You are a fractal being living in a fractal world. The story of fractals reminds us that mathematics is a journey of discovery, not invention. Mandelbrot didn't invent the set that bears his name. He discovered it. It was always there in the mathematical landscape, waiting for computers powerful enough to visualize it and minds curious enough to explore it. Before Mandelbrot, mathematicians had glimpsed pieces of fractal geometry. Julia sets, explored by French mathematician Gaston Julia in the early 1900s, are closely related to the Mandelbrot set. The Cantor set, discovered in the 1880s, is a simple fractal on the number line, the Pinot curve, which fills an entire square while still being a one-dimensional curve. Shocked mathematicians in 1890. But these were seen as pathological cases, mathematical oddities, exceptions to the rules. Mandelbrot's genius was recognizing that these weren't exceptions at all. They were glimpses of a deeper truth, that nature's geometry isn't the geometry of Euclid with its straight lines and perfect circles, but the geometry of fractals, with their roughness and self-similarity. Mandelbrot gave us new eyes to see the world. Once you understand fractals, you notice them everywhere. You can't look at a tree, a coastline, a cloud, or a river the same way again. You see the hidden patterns, the self-similarity, the infinite complexity emerging from simple rules, and you realize that the boundary between order and chaos, between simplicity and complexity, between the mathematical and the natural, is not a sharp line but a fractal frontier, infinitely detailed and endlessly fascinating. The fractal revolution continues today. Scientists use fractal analysis to study everything from the cosmic web of galaxy clusters to the quantum foam of space-time. Engineers design better materials and structures using fractal principles. Artists create new forms of beauty, and mathematicians continue exploring the infinite frontier of fractal geometry, discovering new sets, new patterns, new wonders. In the end, fractals teach us a profound lesson about reality and our place in it. They show us that the universe is far richer and stranger than our intuition suggests, that beauty and mathematics are intertwined, that complexity can emerge from simplicity, and that patterns repeat across scales from the tiniest to the cosmic dot. And perhaps most importantly, fractals remind us that there's always more to discover. No matter how far you zoom into the Mandelbrot set, there's always another level of detail waiting. No matter how much we learn about fractal patterns in nature, there are always new applications to find. The journey into fractal geometry is itself fractal, infinitely deep, endlessly rewarding, forever revealing new beauty at every scale. Just as you can zoom into the Mandelbrot set forever and never reach the end, humanity can explore mathematics forever and never exhaust its wonders. So the next time you see a fern, a snowflake, a coastline, or a cloud, remember, you're looking at a fractal, a piece of infinite complexity created by simple rules, a bridge between mathematics and nature, between order and chaos, between the finite and the infinite. And remember Benoit Mandelbrot, who asked simple questions about coastlines and opened a window into mathematical beauty that will inspire wonder for generations to come. When you send an encrypted message, you're using mathematical ideas related to those Turing employed against Enigma. When you use a computer, you're using a machine whose theoretical foundation Turing laid. When you wonder whether AI can truly think, you're engaging with questions Turing first formulated. The mathematics that saved the world during World War II continues to shape our world today. From cryptography to computation to artificial intelligence, Turing's legacy surrounds us. The secret war fought at Bletchley Park with logical machines and mathematical insights proved that ideas can be as powerful as armies. That mathematics can be a weapon for good, and that one brilliant mind, armed with logic and determination, can change history. Alan Turing's story is ultimately one of hope. It shows that knowledge matters, that science matters, that thinking deeply about hard problems can have profound real-world impact. In our age of misinformation and anti-intellectualism, remembering Turing reminds us why rigorous thinking, mathematical reasoning, and scientific inquiry are not luxuries, but necessities. The next time you use a computer, spare a thought for the young mathematician who imagined universal machines before any existed, who turned abstract logic into practical tools. That helped win a war, who asked whether machines could think long before anyone else took the question seriously, and who paid a terrible price for being ahead of his time. Alan Turing used mathematics as a weapon to defend freedom, and in doing so, he gave us the tools to build the digital future we now inhabit. His story reminds us that mathematics isn't just about numbers, it's about understanding the world and having the power to change it.